Symmetry is changing one thing, but the final result will always remain constant.
Like flipping 7 plus 10, but having a constant 17. Similarly, symmetry in physics shows that the same constant physical laws will apply to any moment, location, or orientation, just like driving laws will be the same no matter where, when, or what you are. And that's it for these intuitive symmetries.
In fact, it was proven that other symmetries formed by the combinations of the space, time, and or rotational symmetries wouldn't even resemble our own universe.
But wait, this theorem didn't include spin. It all began with two Dutch physicists who were confused by their experimental data, which only electrons with particular magnetic properties could solve. Noting that charge in motion equals magnetism, they soon discovered that only spin could fulfill the specific magnetic requirements.
It's an essential property of the electron, much like its mass and charge, and it's found that spin is essential to all particles of the Standard Model. Now, spin revealed another kind of rotational motion that wouldn't exist in classical physics. So, just as rotational motion allows for treating all spatial orientations the same, could spin lead to another symmetry? The answer is yes. With spin, exactly one more symmetry is possible in our Standard Model, allowing us to solve many discrepancies.
The symmetry that binds these spinning particles together is supersymmetry.
Supersymmetry puts matter and forces on equal footing. In supersymmetry, all fermions, matter particles that form structures like yourself, require partner boson particles, which rather act upon those structures. These partners are called superpartners and are put into symmetric equations, meaning that we can switch the equations for each partner particle, but the effect they have on the world will remain constant. It's this property of supersymmetry that allows for treating both matter and forces identically. However, scientists have found that none of the known particles can be grouped up like this. The amount of particles then must be doubled so each fermion has a boson and vice versa, but more particles really repelled some scientists to reject the idea. However, supersymmetry still helps us solve some physics problems. One comes from technical issues with quantum processes, which are solved including supersymmetry. The issue arises from fluctuations in space-time. In this frenzy, particle interactions are only consistent with very precise calculations. So precise you can imagine shooting a target on the moon with almost no error. But supersymmetry calms down this frenzy.
As you see, supersymmetry can unlock more secrets of our universe and help us bridge pieces of our understanding of the universe as well. But only time will show if it's true. Following the standard of our history, when our understanding reaches new depths, we're always only just breaking the surface of something far greater than we could have ever imagined.